So now back to a quick recapitulate. So what am I doing? Today, we are just talking about the various aspects of nuclear physics, right? And as I said, you have to understand nuclear reactions, you have to understand interaction of radiation with matter, you have to understand radioactivity, you have to understand nuclear fission fusion, nuclear reactor, accelerators, and detectors, okay? And the starting point is the nuclear structure and composition, and its reactions. So you might feel that we are just doing some hop, skip, and jump, but that's just to develop the base, and then one by one, each aspect of nuclear physics, whether it is reaction, interaction of radiation with matter, or cross section, scattering. I also mentioned scattering to you, and its corollaries like using accelerator and detector will be dealt one by one in detail, and the tedious mathematics dependent or quantum mechanics dependent concepts like scattering, etc., would be dealt with subsequent classes. So quickly looking at nuclear stability, why do protons stay together when positive charges repel each other? Inside an atom, you have this figure, and we have used here the Bohr atom model along with elliptical orbits of Sommerfeld, right? So
Excuse
you
me,
have
ma'am. I'm
yes,
sorry to disturb, but your screen is visible. We can see data, the three good nuclear properties, not the PPT. Your other screen is visible.
just a sec. Let me then. Okay, thank you. Let me now reduce and ask all you all over again, right? So just give me a moment. You should not be sorry to say all this. We are here as the share window is closed, okay? And now I will share my screen again, right? Is it
Yes, ma'am.
okay? So let me share my screen of this one. It is going to have a green colored PPT. If you are not able to view this, please tell me. Can you now view a green colored PPT?
Yes, ma'am. Nuclear stability. Yes, ma'am.
Thank you so much.
No
And thank
problem,
you
ma'am.
for pointing out, because this webinar series for the benefit of the students, it should go the way it leads them to a particular understanding. So quickly go through nuclear stability. So why do protons stay together when positive charges repel each other? So in the figure we have here a schematic diagram of an atom. Inside an atom you have electrons, and here in this picture we are considering a Bohr atomic model where the electrons are moving around the nucleus in various orbits, and they are not circular according to Bohr but elliptical according to the suggestion and the alteration of the orbit's structure shape by Sommerfeld. So Sommerfeld's elliptical orbits are shown here, and the electrons are moving around it, and you have the nucleus at the center. Okay, so we know that the strong force is responsible for the nuclear stability. It opposes the electrostatic force. The movie that I was sharing with you was trying to convey the same idea to you, that why nuclear stability is important, and how we can understand nuclear force versus the electrostatic force. There is no force exerted because of the neutrons in the electrostatic regime because it has no charge. However, the protons, being positive charge, have got an electrostatic force which is positive in nature. So the electrostatic force is opposed by the strong force of the nucleus, and therefore the stability of the nucleus. The strong force is exerted by anything which has got mass. Who has got mass? The protons and the neutrons have got mass, and so they attract the other masses together. And we know very well that nuclear forces are predominant over short distances. This is just a recapitulation. I'm sure you all are very well versed with it. So nuclear forces act only on short distances, and neutrons act as insulating, the binding material for the protons. Otherwise, they would just repel from each other, away from each other, and move away. Neutrons act as insulation since they have no charge, but they have the strong force to bring other nucleons, that is protons and neutrons, together. And as a result, we have this structure where all small balls are as if clinging together. And later on, when we will be doing the course on particle physics, you will be studying in details about the components of neutrons and protons. So this U up and down is what you will see towards the particle physics. So I'm not going to speak about up quark, down quark, and so on. Now, in nucleus stability, what is it that we have to understand in nuclear physics? In nuclear physics, we have to understand the N by Z graph. So number of neutrons are plotted on the y-axis and number of protons are plotted on the z-axis. This is the famous N by Z graph, right? As a general rule, a nucleus will need a neutron by proton ratio of 3:2 or 1.5:1 in order to stay together. Now, this rule is more precise for larger nuclei. Now, let us look at the graph. We can see that the N by Z graph is as plotted here, and you can see 50, 82 and things like this written, which correspond to the number of neutrons for a particular number of proton nucleus. Now, of all the known isotopes of the natural elements that are present in the periodic table, which are about 1500, all isotopes I'm saying, only 250 of them are stable. All of these stable isotopes have an atomic number between 1 and 83. So the stable isotopes of all the elements of the periodic table, the stable isotopes of all the known elements of the periodic table, they are something around 250 in number, which are stable, and their atomic number is lying between 1 and 83. The movie that I was showing you was nothing else but the graphical expression of binding energy. Now, the amount of energy that keeps a nucleus together is known as the binding energy. This binding energy word is also used when we talk about the binding energy used for an electron to be bound to a particular nucleus in the model of the atom. This amount of energy is higher for nuclei that are stable than it would be for unstable nuclei. So if you have stable nucleus, which is for the stable isotope of the known elements in the periodic table, then this binding energy is higher, okay? And it is measured in units, which are known as joules. So if you supply external energy to any particular nucleus, which has got neutrons and protons in it, that energy will probably break the nucleus. And how can you supply this energy? You can do it only by using accelerators. We'll come to that much later. So the amount of binding energy for a nucleus can be calculated using the famous Einstein relation E is equal to mc square. And this equation states that mass can actually be converted into energy during nuclear reactions. So far, nothing new. We know this. So the mass of a nucleus will be less than the mass of all of the protons and neutrons making it up. This you know very well. You calculate binding energy, you calculate mass defect. So if you have, so once again, what is mass defect? The mass defect is the difference in the mass of the composite particles minus the initial particle. The difference is called the mass defect, which is converted into energy if the nucleus is broken up. If the nucleus is broken up. So the mass of a nucleus will be less than the mass of all of the protons and neutrons making it up, right? And this mass defect is what you have to calculate in numerical values, and it is extremely important because it is that mass defect which is converted into energy. So you have several numericals based on this part of the binding energy or mass defect or packing fraction, whatever you might call it. Vaishnav, I cannot read your raised hand right now. Please pose the question later. Is it that you want me to go slower? Let me look. I still can't see the chat box. So I'm hosting right now. Ms. Moinit, can you just see if there is any comment in the chat box, please?
Yes, ma'am. They are saying that the speed is good. Please continue.
Yeah, because you see, you know these things. We have to quickly recapitulate what we know and then create space for what we do not know. Create space for what is not clear to us. So if the mass that changes is very small, will it release enough energy? So energy is change in mass called the mass defect divided by the speed of light square. So very easy, very simple, and we know it. So nucleus stability, the binding energy calculation requires the knowledge of the speed of light, we know it. The square of it, we know the value. Conversion factor from AMU to kilogram, which is 1.66054 into 10 to the power minus 27 kilogram per AMU. Mass of the hydrogen atom, which is close to the mass of proton, which is 1.007825 AMU, and mass of neutron. These are standard values, and if we know these 5 standard values, then we are able to do any calculation of binding energy for any numerical posed to us of this level. So once again, with the end of this, I will now quickly go to the other slide which I was talking about. What I tried to tell you is that before tomorrow's class, you should give a good revision to Beiser's chapter of nuclear physics, that of nuclear structure, so that we finish nuclear structure and start talking about either nuclear reactions or cross-section in detail tomorrow, right? So with respect to that, I will also point out few more things which I'm absolutely certain you all are aware of. However, this is where I was in my first lecture, and I will just recapitulate it because you must be knowing it well. And if you have any further question regarding where to study and so on, so reading a chapter of Beiser and the beginning chapter of Cohen should be more than enough. If you do not have Cohen, you can read any other book but of this level, right? So now continuing to talk about binding energy itself, the atomic masses of nuclei and electrons. So mass of the nucleus multiplied by c square, this is what I was talking about just now. Mass of the atom, capital M, c square, minus z, m0 c square, where m0 is the mass of the electron multiplied by square of the speed of light, and Bez, where Bez is the total binding energy of all the electrons. So in order to find out the total energy, the atom's energy is then this value, which is shown by my mouse, subtracted with this particular section of Z m0 c square, where Z is the number of electrons or protons in a nucleus. Now this binding energy of all the electron comes out to have a dependence of 15.73 Z to the power 7 by 3 electron volt. This binding energy is small compared to the total mass. Let us consider quickly a beta decay. What is beta decay? Beta decay means that any particular parent nucleus will undergo decay and emit a beta minus particle during the reaction or during the process. So let us take the beta decay of 14 carbon. So 14 carbon decays into 14 nitrogen and gives out a beta minus, which you can see here in this equation, along with anti-neutrino and some energy. This particular reaction is exothermic in nature because energy has come out in the, where was I? Yeah. So in the decay of the beta decay of 14 carbon, the 14 carbon gets converted into 14 nitrogen. There is a beta minus particle which is coming out, or coming out from 14 carbon as a decay procedure, plus anti-neutrino plus energy. While studying radioactivity in detail, we'll find out why the presence of anti-neutrino is essential for beta minus decay. Why without an anti-neutrino, beta minus decay is not possible. And during nuclear reactions, we will study about whether, not whether, it is an exothermic reaction and therefore energy is liberated. And we will have to calculate the energy liberated through the Q value of the reaction. So what is happening? Energy is equal to mass of the 14 carbon minus mass of the 14 nitrogen. Let us take another example of positron decay. So 64 copper decays into the mother nucleus of 64 copper decays into 64 nickel with the along with a beta plus particle which is coming out of this procedure, which is the decay of copper to nickel. Plus there is not a neutrino, it is a neutrino and not an anti-neutrino. So beta minus decay is accompanied with anti-neutrino and energy exothermic reaction, whereas copper into nickel, this transformation requires a beta plus decay with neutrino and energy. So this is also an exothermic reaction. So these particular reactions which are written here, similar few ones should be there embedded into your mind regarding beta minus decay, beta plus decay, alpha decay, and at least some simple ones for the gamma decay. So how do we calculate the energy? The energy will be the mass of the 64 copper, which is the mother nucleus, minus mass of the daughter nucleus, which is 64 nickel, minus 2m0 C multiplied by C square. So for a general reaction, let us consider 56 iron bombarded with 4 helium, which is the alpha particle. So 4 helium is nothing else but an alpha particle. We have this simple reaction, and this 56 iron, when bombarded with 4 He, which is an alpha particle, we get 59 cobalt, sorry, along with a proton being liberated, and plus energy. So again, an exothermic reaction whose Q value will have to be calculated. What is Q value? Q value is a parameter in nuclear reactions which gives us an idea whether energy is absorbed by the system or it is emitted in the procedure of the reaction. So Q in this case will be equal to, Q is energy, so we will be multiplying with C square. Let us look at the quantity inside the brackets. What are we doing? We are going to have first the initial constituents, that is mass of iron plus mass of 4 He, that is alpha particle, and this total mass is greater than the mass of 59 cobalt plus mass of proton. These two, if they are placed in a bracket, then there will be a minus sign outside. If you remove the bracket, then you have minus M59CO minus mass of 1H. So these two minus signs are coming because these two quantities together their masses must be subtracted from iron and alpha particles mass. And then this whole mass, reduced mass, must be multiplied by C square in order to calculate Q value of the reaction. Which reaction? This general reaction which we have considered, where an alpha particle is bombarding a iron nucleus. So suppose we say calculate the energy release in the beta minus and the beta plus decay of 64 copper, then what would you do? You can see the beta minus and the beta plus decay of 64 copper, and similarly copper decays into zinc by emitting a beta minus particle and an antineutrino. You can write this reaction and then you can calculate the energy release. Now these simple equations are extremely easy, however relevant and important for this particular, once again they are relevant and they are important for this particular course where we are going to study about different reactions. So what do we have to do? The first thing that we have to do is, the moment we read about any reaction, the first question that must race into our minds is that, is it exothermic? Is it endothermic? If it is exothermic, then what is the order of the energy released? If it is endothermic, how much energy is to be supplied? And this calculation must race in our mind while we study any nuclear reaction. So these are just simple examples. You will find 1,000 more in the material that I will supply to you. In 64 copper, next equation, beta plus decay, then you will have what? 64 copper decays into 64 nickel and emits a beta plus particle along with it and a neutrino. So how will you calculate the energy release? In the similar manner as you can see above. So 65.421 minus and all these plus and minus you can do yourself and calculate the energy. Let us look at the order of the energy. The energy released in beta minus decay, it is about 0.578 million electron volt. Round it off, 0.6 million electron volt. Further, near half of a million electron volt. What is the energy released in copper beta plus decay? 0.653 million electron volt. Round it off, 0.7 million electron volt. Yeah, little bit more than half of an MeV. This is the order that must stay in our mind in order to solve certain kind of numericals which actually do not require any rigorous calculation. The order of the quantity in the physics. What is the power? By order, you know what is order. So 10 to the power how much? Yeah, in a certain unit, obviously. That idea in any unit should be embedded into your mind. What is the order of the energy released in such and such reaction? And this cannot be memorized unless you embed it into your brain while studying the entire course. This facilitates not only in answering several question answers, that might be posed to you in any examination, it also gives you a feeling of what is the kind of energy involved in any kind of a nuclear reaction, nuclear decay, cross-section calculation, and so on. So by convention, Q beta minus is the energy release and Q beta plus is the energy released plus 1.022 MeV. We will go into detail of all this all over again. I'm just giving you a kind of a recapitulation, refreshing your knowledge, as well as forcing your brain to ponder on these points. So we see that Q beta minus is energy release is added for beta plus. Why? We will go into details in the next class. So Q beta plus is 1.675 and Q beta minus is 0.578. So round it off 0.6 MeV. That is 1.7 MeV at least. So the energy released in a beta plus decay is much higher than that in beta minus decay. So difference between the mass of the nucleus and the constituent nucleons is called the binding energy. It is the energy released if nucleons form the nucleus. So the equation of binding energy is extremely simple and does not require any rigorous mathematics. You can do it, and I'm sure you are well adept in the art of doing it. We can calculate average binding energy per nucleons also. Okay, and the mass, which is excess, is calculated as MAZ minus A. So I think this particular portion is not difficult, and the binding energy graph, which is visible here, where the average binding energy per nucleon is plotted against the mass number A, we can see very well that first of all it is increasing, reaches a final high level, and then decreases down. In my tomorrow's class, I'll be discussing regarding binding energy, the stability of the nuclei, and how this binding energy curve gives an insight into many facets of nuclear physics. So, binding energy of an even A nucleus is generally higher than the average of the values for the adjacent odd A nuclei. What is odd A? Odd mass number. So, even mass number nuclei and the odd A mass number nuclei. This even odd effect is more pronounced in graphing A versus the binding energy from the addition of one more nucleon. Now the question is, the very exothermic nature of the fusion of hydrogen atoms to form helium, which is the process, as we know, that gives rise to the sun's radiant energy, follows from the very large binding energy of 4H. Second point, energy released from fission of the heaviest nuclei is large because nuclei near the middle of the periodic table have higher binding energies per nucleon. Just check this again with this particular graph. So you see the middle A values are having a higher binding energy. So something like 50 to 100, you see the binding energy, average binding energy per nucleon is higher for these elements. So whatever I have listed down in this particular slide, 4-5 points, they have to be dealt in detail, first qualitatively and then in a quantitative way. So that is fusion, which is going on in the sun, and if we now talk about fission, then energy released from the fission of the heaviest nuclei is large because nuclei near the middle of the periodic table have higher binding energies per nucleon. Okay, the maximum in the nucleus stability curve in the iron nickel region, A56 through 59, is thought to be responsible for the abnormally high natural abundances of these elements. Why are these elements so predominant on Earth? It's because they are really stable. So listing out these 4-5 points and quickly going through this, what I want to point out is that the understanding of fission, the understanding of fusion, the stability of the nuclei, and the predominance of many elements on Earth's crust is all related to the binding energy of the nuclei, and hence a good understanding of the binding energy is extremely important in case you want to understand nuclei and its behavior and their availability on this planet. So So we'll go into detail about, so you know that if it is n is even odd, then what is that? So as z increases, the line of stability moves from n is equal to z, that is n by z is equal to 1, which is that n by z graph. I'm talking about this graph. Sorry. Okay, it's not here. It was in the other PPT that I showed, n by z graph. So from n by z is equal to 1, if you keep on going to the higher atomic number in the periodic table, then n by z goes to 1.5. And this is the influence of the Coulomb force. For odd A nuclei, only one stable isobar is found, while for even A nuclei, no stable odd or nuclei are found. These points or the sentences listed here are not statements for you to gobble up and retain in your memory. These are the checklist that while studying nuclei, we must ponder upon these and find out the real reasons for their behavior, either qualitative or quantitative. Right? So now, in the binding energy, the volume of the nuclei are nearly proportional to the number of nucleons present. Now, nuclear matter is quite incompressible. You cannot compress the neutrons and protons and ask them to fit into smaller and smaller places, smaller and smaller volumes available. Total binding energies of the nuclei are nearly proportional to the number of nucleons present. That means there's some kind of a saturation. A new saturation character is what? A nucleon in a nucleus, that means either a neutron or a proton, can apparently interact with only a small number of other nucleons. You know, so if a nucleus has got, say, 50, each and every neutron and proton is not going to interact with the rest of the 49 nucleons present there. Therefore, we can approximate our understanding of the structure of the nucleus by a liquid drop model. And then comes the concept of liquid drop model, and then other models like shell model, Fermi model, and so on. So I will not go into detail right now into this because this requires some continuity for at least half an hour. I stop here with the words that whatever I've said till now is part of a graduate course of nuclear physics, and therefore you are advised to come up till this level so that we can move ahead and delve deeper. In liquid drop binding energy model, liquid drop and shell model and Fermi model will be touched tomorrow term by term, and will also give you details of what are the representations and what are the meanings of these terms. I'm sure you know them, but we'll just touch them all over again and then talk about stability. So this is, I'm just showing you the portions that we'll be doing tomorrow so that you know that we are going to understand all this. And then the potentials would come after that. So with these words, I'll stop my sharing, right? And I know I have kind of rushed through this portion, but this is essential because of two reasons. First of all, this is part of an undergraduate course, and I'm sure you are aware of it. And the third thing is that we cannot dwell too much on it. However, if you have any questions, you are most welcome to ask it either through our common groups or through email. And if you need any book, also you're most welcome. So Ritu Nain, yes, which books? So again, for every subject I provide you a ladder, and you will get a ladder even for this particular subject. You'll get a ladder for atomic and molecular, for nuclear, for StatMech I've already given, and some such at least 7-8 subjects. You'll know which book to read when and so on. So today the thing that you have to do is read the chapter of nuclear structure of Arthur Beiser, Concepts of Modern Physics, and you have to read the first chapter of Cohen, Nuclear Physics. I'm sending the name of the book, etc., on the group, and you can note it from there. The syllabus that I asked you to download from University of Delhi's website has all these books written in a serial order. Even then, I would still provide you on your group. So am I clear? The book is being told to you. The names are being told to you. For today, you have to read these 2 chapters and can become well versed with it by tomorrow. So that we go a little bit deeper, because from 15th onwards, you'll have faculty from Delhi University, main campus teaching you, and they would not sit with you on very, very small things. And it is my duty now to bring you up to that level, right? Anything else on the chat box? So with these words, I would now stop